Good morning. I'm Bruce, and welcome to my Baptronics Mountain Labs here in Colorado. Today on the bench, we're going to introduce you to a Fluke 1953A counter timer. This particular unit is in beautiful condition, as you can observe here. And as you're going to see, it's also a fantastic performer. At the moment, we're displaying a 50 million hertz count, plus or minus 1 hertz on the display right now, and that's coming from my rubidium cowled master oscillator that's up top side here. We used it to zero beat the crystal oscillator that's within the Fluke. We're going to give you a look at that in a minute too, because it's something to see. When you're looking for a counter for your bench, there's some important things to note and look for. One would be the measurement range, and that would be the frequency range that you could cover with the unit. You want to make sure that it covers the range that you're interested in. Another would be the number of digits or resolution that you get out of the measurement. Accuracy of the unit and its stability, repeatability, maybe other functionality like measuring periods and time intervals and things like that expands the usefulness of the unit. Its sensitivity, got to be able to resolve some pretty sensitive incoming frequencies from some circuits, and others you're going to just bombard the unit with large signal swings, and in that case you got to be able to adjust and handle that as well. And then finally, you want to have something that looks good. So I got to tell you, this particular unit has all of that. We're going to get into that right now. The unit has 3 input channels. We've got A, B, and C. A and B are accessible from the front panel. This is A, here's B. We have the trigger level controls. This would be your sensitivity controls for channel A and B. We have an attenuator times 1 times 10 for both channels. AC and DC switches, and we can adjust for the slope. Either we have a positive or negative slope for the trigger action. We can measure the frequency of A, and we have what they call a frequency of C. C channel is accessible from the rear of the unit. We'll show you that in a few moments, but C channel can measure from 50 megahertz up to 520 megahertz with a 50 ohm input. That gives you quite a range. Channel A can measure from DC to 125 megahertz. Same, I see for channel B, it's DC to 25 megahertz. Both of them with a 1 meg ohm input. We have 1, 2, 3, 4, 5, 6 gate periods, ranging from 0.1 millisecond to 10 seconds. And we have a reset control. We've got continuous or triggered mode that we can run this thing in. It's really, it's got a lot of functionality. We can separate the 2 channels A and B, or we can use a common between the 2. Tie them together. A and B are used to produce things like the ratio, so you can measure the ratio of a frequency on channel A to a known frequency on B, and it'll tell you how many times A can be divided by B, for instance, the ratio. We can measure the period of A. We can do the time interval between A and B. We can gate A, it's called A gated by B, and then we have a self-check function, which we'll go ahead and just demonstrate right now. So right now we're taking a look at the 10 million hertz internal oscillator, and as we change our range we can see that we'll drop a 0 for each range, and this is a way of checking our ranges and our master oscillator. I'm going to open it up and we're going to give you a look at the interior of the thing and make a few comments, and then we'll continue. So hang on, I'm going to open her up. Okay, I've turned the unit around and I've removed the top so we can do a little investigation of some of the other features of the unit. Here on the back we can see we have access to channel A, channel B, and here is channel C, which extends us up to 520 megahertz. We have the level of A, which is sensitivity level from that trigger control, level of B. We've got a marker output. We've got the gate output. We can take a look at the clock output, the internal clock, use it to trigger something else. Or we can go from internal to external clock, and we can use a bench standard to run the unit. Normal or burst mode. We have the options plate here. We see it indicates options 2, 14, 12, 16, and 20. But the option for the remote control no longer applies, as the remote control boards were defective and were removed. So for most of us that's not a problem. Anyway, we wouldn't have the control units to be able to do that, and it's better that we just have a working counter. Okay, let's take a look at the inside. Oh, by the way, these are the dust caps off of the rear unit inputs. They go on like that. Take a look at the inside. We see some high quality workmanship, fiberglass boards, silvered traces, and of particular interest here, well, here's your 520 megahertz board here. Something that doesn't come with the base unit. Your controls for your trigger sensitivity, function control switch, display panel, and then of particular interest would be this oscillator. This is an Ovenaire model OSC 49-65, 10 megahertz, made in Charlotte, Virginia by Kitty Corporation. And it is the third best out of 4 oscillators that were provided for this unit. It is capable of producing a 10 megahertz signal with an aging rate of 1 times 10 to the minus 7 per month, stability of 1 plus or minus 1 times 10 to the minus 8 over a 0 to 50 degree centigrade temperature change. And that gives you some fantastic stability and accuracy when it's properly calibrated, which it has been. So I wanted to point this out. This particular feature it could easily have cost another couple of $100 to the unit. If you were to try and buy an oven controlled crystal oscillator like this, you could easily spend $30 to $50 on eBay purchasing a used one. And this one has it all mounted internally. What that does is it takes an otherwise standard piece of equipment for a bench, which can be good, and it turns it into a true bench standard. Anything you want to know about the frequency measured with this unit, you know is going to be accurate. And you can use it then to calibrate other pieces of equipment with confidence. So let's go ahead, hook it up, and we're going to measure some incoming frequencies, and then we'll close out. Okay, we're back to looking at the enclosed unit. We have the 50 megahertz signal coming from this PTS 500 unit here. Magnificent unit that produces very precise frequencies, selectable by knob. So what we're going to do, we're just going to give this thing a few different frequencies to measure. Let's begin by going to 40 megahertz, 30, 20. Okay, now with 20 megahertz, if I was to add another 100 to that 20, then I'd be within the range of channel A. So let's do that. So we go now to 120 megahertz. Okay, so here we can see 125 megahertz coming in on channel A, which would be the limit of its capability according to specifications. So let's go ahead and drop this 5 off, and then take it to 110, 100, here's 50 again, 40, 30, 20, 10, here would be 9, let's go to 5, and let's save ourselves some agony. Go to, that's 300 kilohertz right here. Which at this point we'll have to change generators. So my signal generator on the low end drops off at 300K. So let's go ahead though and take a look at channel C and demonstrate the 500 megahertz capability. Okay, we now have moved our input back to A, and I am running from this HP 3320B frequency synthesizer. This synthesizer focuses on frequencies below a megahertz, and we'll use this to test our low end. So right now we're feeding in a 1.99 megahertz signal, and that's exactly what we're displaying. Our range switch is on the 10 milliseconds per gate. We can raise it to 0.1 seconds, and we see that we shifted over a 0. We're now reading 1990 kilohertz. If we go to 1 second, we see again 1990, but we got 0.010 showing in the display, so we picked up another decade. And we could go to a 10-second average, and that'll give you one more decimal place. But you got to wait 10 seconds between the readings in order to display the results. And there we go. When you get down to frequencies that are starting to get lower, sometimes a direct read like that, I mean, if we're going to wait 10 seconds, that's a long time between intervals. It might be more beneficial to take a look at the period and measure the period of one cycle and display the results on the screen. We can take a look at that. And here we see that we're updating. If you watch the gate light, that's how frequently we're updating our display screen in the period mode. And we see we have a period of 0.502511 or 10. You got one digit that you could be flashing. So our readings are being updated much quicker and we're getting some decent accuracy. You take the inverse of that, and you've got your frequency. Okay, so I took the inverse of the reading, and it comes up to 1.990006189 hertz. And if I go back to reading frequency again, and we give it the full 10 seconds of count, we should probably give it 2 cycles of a 10-second count, just to compare. I got 199000025. Let's see what we get on the next count here. 20. I was able to read my period to 1.990006, and we got 0001 on the frequency display. So slight difference in between the two readings, but as you can see, the update for the period was much quicker. Response was much quicker. The point is that on the lower frequencies, you may well want to get a much faster read, and period would be the way to go. Let's take a look at a ratio. Well, let's see. We did the period already. Let's take a look at the ratio of A to B. We're gonna feed a signal in on B. Give me a moment to set up. All right, so we have the 1.99 megahertz signal coming in, being measured from the HP. Let's drop the 1 off, and we are now at 990 kilohertz. And let's go down to 5. So now we got 590. Let's go down to 90. There's 90. Let's change our range. And go back to 90 again. But let's go to 9. All right, now we see that we've only got 3 significant figures here. That's because I got a 0.1 second gate time. Let's go ahead and turn our gate time up to 1 second. We'll pick up at least another decimal place. We see we've got 9 kilohertz to 3 places, and if we go to a 10 second, we'll pick up another decimal place. And you always want to give yourself at least 2 readings, although in this case it looks pretty good. 9 and 4 zeros, so we're 9 kilohertz to the 100 millionth place. But let's instead of having to wait 10 seconds for every cycle, we don't really want to do that, right? Maybe I drop down to a period measurement, and a period of A then becomes something we can measure much faster. We see that we have 111.111 microseconds. And if you were to do the math, you'd find that the 111.111 microseconds translates to 9,000 hertz, 0.009, something like that, or better. So, and we're updating every 10th of a second here. Okay, so let's go ahead and drop the frequency down lower. Let's go to 900. Oh, let's take our period back up. We'll go to frequency again. We'll try and read that directly. 1 second interval. There's 900 hertz. That's 0.9 kilohertz. Let's go to 590. Go to 90. So we're reading 9.09 kilohertz, which would be 90 hertz. 80. Let's drop her down to, well, there's 40. And 10. Okay. All right, here we have 100 hertz coming in. If we take a look at the period measurement, and we see that we have 10.000 milliseconds. So that would be 0.010 000, and we take the inverse of that, you get 100 hertz. Go back to frequency and increase my range. One reading a second. Let's go ahead and drop ourselves down to 10 hertz. There's 10. And how about we try for 1, huh? And there's 1 hertz. Now you notice we got one significant digit. It's 0.001. That's the. I could raise myself to a 10-second average. Let's go ahead and do that. And we should see ourselves at the end of 10 seconds. There we go, 0.001 kilohertz or 1 hertz. Let's go ahead and take a look at the period reading on that. Okay, we've got 1001.3. Yeah. So let's go ahead and put that in. We've got, that's in milliseconds, so that would be 1.0013. Take the inverse of that, and we've got 0.9987 hertz. So round that up, that's 1 hertz. All right, so we've taken a look at the period. Let's go ahead and set ourselves up for a ratio of A to B, and we'll play with that a little bit. All right, as you can see, I've added a second input line on B, and I'm driving that from this Hewlett-Packard 8640. I've got a 5 megahertz signal on there, so we just understand what's happening. The PTS is putting out a 10 megahertz signal to channel A. So we're taking a look at the frequency ratio of A to B, and we see 2 point, and it's all zeros. So it's 2 to 1. A is twice B. B is 5 megahertz. If I know B, then I know A. That's essentially what the ratio does for you. Let's go ahead and let's go to 50 megahertz, and we see that our ratio now becomes a 10. And we could go to a 10, well, in this case it'd be a 1 second average. There's our 10. So the ratio is working. And they got something called the time interval of A to B. Okay, in the time interval between A and B, the way I'm going to test this, what it does, you get a trigger pulse, either positive or negative, depending on the slope that you pick on the trigger in channel A. That starts a counter that counts in microseconds, and it'll count until it sees a pulse come through on channel B to stop it, and then it'll give you the time interval between A and B. This would be like if I was maybe say physically looking at a race. I had a photocell that created the pulse at the beginning of the race, and then I counted the number of microseconds until I see the end. The way we're going to test this is I'm going to go ahead and put a signal on channel A, and for each positive pulse that I get on A, they'll start the cycle counting. If I allow it to look on B for the next pulse to cancel it, that'll be one full cycle. So in essence, I'll be reading the period of my signal. Then, if I was to take the slope on the on channel B and put it negative, and I see I'm going to take a look at when the cycle goes to the negative pulse, that would be half of the incoming time interval for that pulse, and we'll see the measurement go from a period measurement for the cycle to half of the period, half the cycle in essence. So let's go ahead and take a look at that. We've right now got 500 kilohertz. We're going to adjust it to make it as exact as we can. Alright, there's 500 kilohertz on my HP. And what we see right now for time interval A to B, I've got 20 milliseconds, 0.002, which corresponds to 500 kilohertz. If I change my my trigger slope to the negative, then I'm going to trigger on half of the incoming waveform, and I see my time interval drop to 10 milliseconds. This is what I expected. And then finally we've got A gated by B. Now what happens here is we're going to count what comes in on A during a time period that we measure on B. And let's take a look at that. We've got a 500 kilohertz signal coming in on A. We've got a 1 hertz signal on B. We're going to count for every half cycle of what's on B. So for every half a second, we're gonna see what's coming in on A. Since we got a 500,000 hertz coming in on A, every half a second we should see about 250,000 hertz roughly. So let's go ahead and we'll reset this thing. There's 253,506, 760. So it's going up about 250 kilohertz every pulse. Let's try it again. 253, 506, same thing. So we're counting the number of pulses coming in on A as gauged by the signal on B. And that's working too. Finally, we got the self-check. Let's go ahead and start at the highest or fastest gate time. This is 0.1 milliseconds. So essentially, we would be multiplying everything we see on there by about 10,000. So we've got 1,000 times that'd be 10 cubed times 10,000, which would be 10 to the 4th. So that'd be 10 to the 7th, which would be 10 million. So we're reading 10 million hertz here. So let's go 1 millisecond. So now we're going times 1,000. So 1,000 thousands is 10 million. Here's 10 milliseconds. So we're now multiplying by 100. Add 2 zeros to that, you get 10 million. 0.1 second, you multiply by 10, you get 10 million. 1 second, we get 10 million even. And then finally 10 seconds, we should see 10 million point zero. But you gotta wait 10 seconds. And there we go, 10 million. You got an extra zero on there. So that's the self-check feature. It checks all of the digits and then it takes you through all of the ranges. So we're good. So, for some lucky guy out there, you're going to be able to win the bid on this Fluke 1953A. And in the package, I'm going to include the user service information PDFs, and I'll even throw in a set of beginner leads so that you can get started and go for it. So thank you for listening and taking a look at this thing, and I think you're going to find it to be a wonderful piece of equipment. So.